Hello, today I'm looking at M3 International A-Level, May 2014. This is question 6. So I'm given a particle of mass m is attached to one end of a light elastic string of natural length 6a and modulus of elasticity 9 mg. The other end of the string is attached to a fixed point A on a ceiling. The particle hangs in equilibrium at point B, where B is vertically below A, and AB is equal to 6 plus P multiplied by A. In part A, show that P is 2/3, and this is 2 marks. So here I'll begin by drawing a diagram of what is happening. So I have this fixed point A on the ceiling, the string is hanging down, I'll have the natural length 6A, and then I'll call this extension, as it's hanging in equilibrium, x0, and so my particle will be at the bottom here. Separately, I'll draw a diagram that shows the forces acting on the particle. So there will be the weight, which will be the mass times gravity, so mg in this case, and the tension upwards, and I'm using the formula lambda times the extension over the natural length for the tension. So lambda, the modulus of elasticity, is 9 mg divided by L, which is 6a, multiplied by the extension, which is what I've called x0. And here there's no acceleration, so I know that forces up will equal forces down using Newton's second law. So I have 9 mg x0 over 6a equals mg. So I can see I've got mg on both sides, so I can divide both sides by that. I can see there's a factor of 3 that goes into each of these. 3 goes into 9 3 times, 3 goes into 6 2 times, and so now I rearrange this to give me, I'll multiply both sides by 2a and divide both sides by 3, and so I end up with x0 is 2/3 a. So AB is going to be 6a plus this, and so I get that taking a out, 6 plus 2/3. And so there we can see that P is 2/3. Therefore P is 2/3 as required. Okay, so that part of the question is worth 2 marks. Then it says the particle is now released from rest at point C vertically below B, where AC is less than 22/3 multiplied by A, and show that the particle moves with simple harmonic motion. So here what will happen is I'll do a new diagram. So I've got my 6a, the natural length, I've got my x0, which I know is 2/3 a, and then as well as that the particle is going to be extended by a value of x. Remember, x is the extension when we're looking at simple harmonic motion from the equilibrium position. So looking at the forces that are going to be acting on the particle this time, I'm now going to have a force of the weight down, and upwards I will have the modulus of elasticity divided by the natural length multiplied by the extension, and this time the extension is going to be x0 plus x, so 2/3 a plus x. And as x is measured from the equilibrium position downwards, the next double dot will be measured in the same direction, and so I'll write x double dot acting downwards. So now, again using Newton's second law, as the acceleration is downwards, I'll do forces down minus forces up equals mass times acceleration. So forces down minus forces up. The 9/6 can simplify to 3 over 2. And that will equal the mass times the acceleration. Okay, you'll see I have an m everywhere, so I can divide through by m, and so multiplying this out I get g minus, here the a's will cancel, the 3's will cancel, the 2's will cancel, so I'll be left with g, and here I'll get minus 3g over 2a multiplied by x. And so these two bits cancel each other out, so I'm left with x double dot equals negative 3g over 2a x. And so I have proved therefore that this is simple harmonic motion with omega is this thing square rooted. Okay. So that part of the question is worth 4 marks. Then it says find the period of the motion. Well, to find the period of the motion, I use the formula. The period t is 2 pi divided by omega. And so here I can do 2 pi divided by the omega that I identified here. Dividing by this is like multiplying by the reciprocal. So the 3g will end up on the bottom and the 2a will end up on the top. So I can just leave my answer like that. Okay, so that is worth another 2 marks. Then in part D, it says explain briefly the significance of the condition AC is less than 22/3 A. So 22/3 A, let's see what that means. 22/3 A means so this means that we've got 7A and a third A. So if we look at what this means in terms of what x would be, so if I do 22/3 minus 6 and 2/3, hang on, oops. Then that means, so 22/3 minus 6 and 2/3 multiplied by A would give me 2/3 A. So that would mean that the extension is 2/3 A, the extension from the equilibrium position. And so therefore this is extended less than the value of x naught, which will mean that basically the particle will move in this area here as opposed to being stretched more than that, which would mean that when it gets to here it would carry on moving up. So it basically means that this string is always extended. So the significance of this condition is that the string is always extended. Okay, and that is part D. Then it says point capital D is vertically below A, and AD, so remember A was the point on the ceiling, so here was A, and so this will be kind of longer than that. The particle is now released from rest at D. The particle first comes to instantaneous rest at the point E. Find in terms of A the distance AE. Okay, so because we needed for simple harmonic motion this particular condition, then that means now I need to kind of forget about all of the simple harmonic motion stuff that I already worked out, and again instead look at energy. So let's just see what's happening at this extended position and work out what would be happening when the particle instead is at E. So what we would have here is A, we've got D, which is down here, and we know that that distance is 8a, and at that point, from the extension of the string would be 8a minus 6a. So when the string is here, then it is extended by 2a. We know that here it's held and released from rest, so we know that there is some kinetic energy. The kinetic energy will be 0, but we do know that there will be some gravitational potential energy. Well, we can say that is 0 at this point, but there is some elastic potential energy. Okay, so no kinetic, no gravitational potential energy, but there is some elastic potential energy. If instead we look at the position AE, so E will be this position somewhere up here, then at E, then it comes to rest, so there'll be no kinetic. There will be some gravitational potential energy, and the elastic potential energy will also be 0, because at that point this string will be slack, because as we talked about before, for simple harmonic motion we need the motion to happen always within here, but now it's being stretched well below that, so it's going to go kind of above this position, and therefore the string will be slack. Okay, so the elastic potential energy at D, so I need to use the formula lambda times the extension squared over 2L. So lambda for this string was 9mg. L was 6a, so 2L is 12a, and the extension, well, the extension of the string is 2a, so I have 4a squared, so the extension squared. And then I know that will equal the gravitational potential energy, so I'll just call that mgh. I'll work out h and then do a bit of fiddling to work out what they actually want, which is the distance from A to E. So I'm calling from D to E h. Here I can divide both sides by mg. Here I top and bottom can divide by 4. 9 and 3 divide to give me 3. And a squared divides by a to leave me with a, so I end up with 3a is h, and then the distance that they actually want is ae, which will be 8a take away h, which will leave me with 5a. Okay, so that is the last part of the question. That is worth 4 marks. So I hope you found that solution helpful. Good luck with your studies, and do click like if you liked it.